Okay, so I'm going to, mostly today, we're going to be looking at simplicial set-valued functors. But first, I'm going to finish off with some more things about set-valued functors, which help to motivate the reasons for starting to look at simplicial sets. Now, so you remember how last time we saw there was the Marek-Cartan functor, and we got the deformation functor from that by modding out by gauge equivalences. And in fact, you can just recover that deformation functor just from the Marek-Cartan functor alone and a universal property. So there's a theorem by Manetti, which is that deformation functor is the universal deformation functor under the Marek-Cartan functor. In other words, we've got the map we defined last time given by taking the quotient by the gauge action. If we had some other deformation functor F, and a natural transformation on the Marek-Cartan functor, there would in fact exist a unique from the deformation functor. And there's a more general way of constructing deformation functors out of functors like this. And that's where Manetti introduces the notion of a pre-deformation functor. So there's a start with conditions that are exactly the same as for deformation functor. So if we've got the product here, the map from A to B being a small extension, then F applied to the fibre product subjects onto fibre product, the images of F. Then we have F preserving products. So those two are exactly the same as you have for a deformation functor. And then the only thing that changes now is behavior under acyclic small extensions. Acyclic. That's where we're saying the kernel is acyclic. And in case you've forgotten what a small extension was, that's where we say that the maximal ideal kills elements of I. So the only difference here between the pre-deformation and deformation is that here we're saying surjective. Whereas for deformation, it had to be an isomorphism. And there's another theorem by Manetti, which is that if you have a pre-deformation functor, there is always a deformation functor associated to it in a universal way. It's universal. Deformation functor. F plus under it. Now, the definition I gave you last time of the way we got from Maroc-Cartan to deformation, modding out by the action of a group coming from. So it was, we looked at the degree zero part of the algebra, exponentiated that to get a group, and to gauge action, which is like an adjoint action. If we're starting from some arbitrary functor, we don't have a way of doing that. But we do have the gauge construction that Jonas showed us earlier. We can do that to any functor. So what happens is, this is just given by so f plus of a is, well, I ought to, maybe I should say, this modulo and equivalence relation from or actually, sorry, I need to be slightly more careful than that. So it's two maps, so we send S to either 0 or 1. And if this thing here looks a bit ad hoc, we can rewrite that. We start with AS ds, but then that's not a local ring anymore. So it's just that, it's that final product, if you like. So this is just, the problem is we've got polynomials in degree 0. So this is a construction that gets us back a local ring again. And so this is actually part of the reason that with Manetti's extended deformation functors, you work with DG-Artinian rings with no sort of allowing negative degrees, because with the chain conventions that I'm using for these things, we've got S is in degree 0. So ds is in chain degree -1. So this isn't something you could do if you only had a functor defined on non-negatively graded chain complexes, so with a commutative multiplication, then this construction isn't available to you because this takes you out of that category. And so and you can. So, and in fact, exactly as Jonas said, so a priori we're just saying the equivalence relation generated by this, in fact, it is a genuine equivalence relation. And I'll probably explain why a little bit, and I'll just complete the picture with this. So there are a couple more things we can say. One is, so another theorem, Manetti. So morphism. Deformation functors. It's an isomorphism. If and only if it gives us an isomorphism on cohomology. And this is the way you prove this is by on an arbitrary element you look at these successive small extensions. And play around with the various properties and work your way up the tower. And then you find you can just reduce to things like that in terms of those exact sequences I was writing out last time. You get the ends of the exact sequence agreeing, and so you put them in those. So now, that. Sorry.
It is written at the end of the.
This here?
Yes.
So it's K plus K epsilon N.
Okay,
so this was the ring where this is a square, so this is an element living in degree N. It's necessarily square zero. And so now, in fact, is that enough for me to give a proof of, yeah, so if I call this theorem A, I can now give you a proof of theorem A by combining these other results, which I haven't. So MCL is a pre-deformation functor. And we've got a map from MCL to DefL. Therefore, there's a map from MCL plus DefL. And now all you have to do is work out the cohomology. And in the case of def, this is a calculation we've done. In the case of this plus construction, it isn't, but it's not too difficult. It's just a slight variant of that one. And we get that in both cases, it's the nth cohomology. It's just the n plus first cohomology of L. Yep.
So when you write def L in this proof, do you mean like the universal deformation functor under MCL?
I mean, the thing I define, so this is where...
or do you mean what you define as the quotient?
I mean, that thing I defined last time, but then, thanks to this theorem, the point is, so they're isomorphic. So therefore, so the thing we defined last time is a universal deformation functor under MCL. This construction gives you another one. Therefore, they must be the same. Therefore, those two, like different ways of defining gauge equivalence, agree. Yep.
How do we know the cohomology of MC plus? Is that the same with MC?
The cohomology of not quite. So the cohomology of MC is, let's see. Is Zn plus 1 of L. If you work it, but then
How do we know the cohomology of MC plus?
it's just a calculation. So you just
Oh, okay.
you just do this with Zn plus 1 of L, and then you do it with Zn plus 1 of L SDS.
In this theorem, the relation is strictly generated by the in only this diagram. You do not need any transfer from other algebra.
Sorry, are you asking whether it's transitive?
Yes, I mean only generated by this diagram.
Yeah, so it's the relation generated by this diagram. Yeah.
Yes, second.
Yeah.
Okay.
Yeah, and so you end up looking at this the quotient of this, and this is you end up getting a copy of Ln in here, and you're just modding out by that. So that's what's happening there. Right, and so now. And this is something I'd forgotten until Jonas mentioned it, but of course, a priori, this isn't the transitive relation. It's just saying the thing generated by that. But in fact, the relation is transitive. And what you do is, so you end up looking at two variables like that, and you mess around with it. Now, and if you're looking at Melech's paper, he writes it out in detail. But what's really happening here is that at this point you're already looking at something simplicial. So the picture you've got is, I'm going to start writing, in fact, I might just start now. I'm going to write this write these in more symmetric ways. So in the first case, it's going to look like a really silly thing to do. We can rewrite this. Starting from the RAM algebra with two generators, S0 and S1. Then forcing the sum of the variables to be 1. And the advantage of that looks a bit silly here, but it means that everything becomes completely symmetric. So instead of evaluating S at either 0 or 1, you're killing one of these two variables. So sending one of them to 0 and the other one to 1. And more generally, what we can do, so we have a version of this for n variables. So I'll make a bullet of delta n got to be each algebra we have n plus 1 generators, so S naught up to Sn in degree 0. And ds naught up to dsn degree, so chain degree minus 1. Such that the sum of these SIs is 1, and therefore sum of DSIs is 0. So one of these variables is completely redundant. So if you're just interested in this as an algebra on its own, you could just get rid of the first variable. But writing it this way shows a lot more symmetry that we want to use. And the reason I've written it this way is that this is known as polynomial derived forms on the n-simplex. So what's happening is this is forms on the hyperplanes. And if you've ever done much topology, so certainly things like singular homology or simplicial homology, you will have seen that if we also require these variables to be between 0 and 1, that's the definition of the n-simplex. Because we're doing algebra, it doesn't make sense to restrict things between 0 and 1, but you could actually build an equivalent theory of singular homology, certainly simplicial, singular homology, dropping those constraints, so building things from copies of R rather than copies of the interval. But just like compactness makes things a bit, lack of compactness makes things a bit messy. And so that means that, these things then have maps between them corresponding to the usual maps between simplices. So you think you've got delta naught as a point, you're used to delta 1 being a line between them, so you've got two maps that way, where you can do the vertex, one going back where you squash things down. Three maps this way for the three edges. Two maps going back where you collapse one of the edges. And then delta 3 I can try and fail, or something like that, all filled in. And then So we get a corresponding picture or diagram with these DGAs of polynomial forms. Just all the arrows going the other way. So we've got a delta naught, which is just k. These were our two evaluation maps we were interested in, sending s to 0 or 1, with a map going back. And then the way you show transitivity is using that algebra, the map's going that way. But also got a couple going back, and so on. So we can carry this on all the way up. So what we have here is a simplicial diagram. So conventional we call these maps. The maps going that way are DIs, and the maps going this way are sigma i's or SI's. Sigma naught. D naught, this one down here is D2. D1 in the middle, sigma's in between them. D3, D's in between them. Sigma's there. So this is a so you can think of each of these as being, so these are functions on n simplices. So we've just got each one of the standard maps between simplices. Each one of those very sort of generosity maps gives us corresponding map going the other way, is function on it. And there are relations between these, which I'm not going to write down. If you've come across simplification stuff before, you'll know what they are. If you haven't, writing them down won't really tell you anything. So there's the most abstract characterization is that this is a functor on the category of sets of the form. So sets of sequences of integers, right? So, and non-decreasing maps between them. It's going to be a contravariant function, isn't it? This is simplification, not co-simplification. But just, yeah, I think for most people, this picture is all you really need. Right, so now, we're in a position to find simplicial functors. So any diagram looking like that is simplicial. So we have a corresponding notion of simplicial sets. So given this definition actually goes back to Hinnage, and this is formality. This is I wrote it somewhere. It was so we can define, and I don't think this is his notation. DGR to simplification, so this the simplification sets. And what you do is at degree 0, you have MCLA, so that's a set. Degree 1, MCFL tensored with the random forms on the one simplex, evaluated at A. Next level up, forms on the two simplex, so on. And so you can see that so what happens is that the deformation function we were looking at is just, it's not as a path component of this, so it's just modding out by the equivalence relation given by these two things here. But in fact, if you look at this whole structure, it has significant advantages quite often over working with those set value factors. So one advantage is that we can actually recover everything just by, so rather than working with DGR, we could work with DG plus R. So we could just work with, just take A to be DG algebras in non-negative chain degrees. It actually turns out that so this extra data down here captures all the information we had previously by allowing negative terms in the DG algebra. And as you probably saw, remember when we were looking at those examples, so both of deformations of a vector space, deformations of an algebra, things behave much more as you'd expect when you restrict to here. So you have the vector spaces don't deform anymore. They have you get automorphisms, and this tells you about higher automorphisms, but you're not getting those slightly counterintuitive deformations, and also things like when we're having curvature with the algebras, like that's not something that crops up if you're working here. So that's one advantage. The main advantage, and the reason people use it, is so in Severan's first lecture, when he talked about when you're trying to do global versions of these, and there's the problem of what happens when you take a quotient, because quotients in algebraic geometry are not usually very nice things. There are sometimes, if you're really lucky, you have a fine quotient, but usually you're taking coarse quotients, and basically what will happen is these functors are never going to be, so these sorts of deformation functors are never going to be representable by any geometric object you want to work with. And also, because you've taken that quotient, things behave poorly under limits. So you can't start taking further products, gluing things together, anything like that. I mean, even to give a really irritating example. So part of the motivation we had was to look at deformations over that formal power series. Now, you could have now, if you think about it, so far I've only been defining things on Rotinian rings. So if you plug in complete rings, there are actually two different ways you can do things. Because we've got both a limit and a quotient. So the natural way to define deformations over this is to take limit of deformations over reduced truncation of things and then mod out by gauge action in the limit. And then there's an obvious map from this to the limit to these quotients. Def. But in general, this doesn't have to be an isomorphism, because inverse limit is not an exact functor. And off the top of my head, I don't know a counterexample, but the issue is there's a lim one issue. So if you think you can prove that this is an isomorphism, check that you haven't just proved that lim one is exact, because it isn't. So the inverse limits are exact because they are. It's really horrible. It's just to do with in this limit here. So it's just surjectivity can fail. So in this limit here, you've got a whole system of solutions where at each point you can take a gauge transformation to get things to match up. But there's no way, but you don't know that you could have, that you can choose those gauge transformations compatibly, that you get a genuine element in the limit. So it's a horrible, annoying subtlety. Whereas that turns out not to be a problem at all if you're working with things like this. Because what happens is that this functor here ends up preserving what we call homotopy limits. And so you can recover the thing you want from this just on Martinian rings. Right, so I think I've sort of defined simplicial sets.
Which of these two is the correct one? The top one or the bottom one?
This one is the correct one. Because you want, yeah. Yeah, I mean, you think about, so deforming an algebra, you want power series. So you want to deform that algebra over the power series modulo change of coordinates. Irritatingly, in this case, having all these ones here, I don't know. It might be quite a convoluted example to actually cook one up where you do have the non-vanishing then one that does become a problem, but there is certainly a potential issue there. And it was, and this actually was something that was only pointed out to me a few years ago, where I'd sort of, I think, if you look in the published version of paper on unifying around deformation theories, I think somewhere I did assume this would work out okay. And so I assumed that Manetti's deformation functors were better than they are. That you could extend them to complete local rings, and there's so the version on the archive is now correct. Right, so there's a remark. The category of simplicial abelian groups. SAB is equivalent to category of chain complexes. In non-negative degrees. And the way the construction works is, start from some simplicial object. You map to something called the double card normalization, where ln of v is v in level n, such that di of v is 0 for all I positive. Yeah.
It's on the left still. Can you put the tensor with the omega also with the a on the right side? Or is it maybe ignore the...
So it was just, the reason I put it on the left is, I rubbed it out. It was exactly the issue with the maximal ideal. So it's, so what you could do instead is have it's just because this thing's defined in terms of the maximal ideal here. So the way I defined it, MCLA was it's MC of L tensor. If you look at Manetti's paper, his solution actually is just to forget about K and only ever work with maximal ideals. So morally, yes, but there's this annoying subtlety. Right, so we've got, so it's chain complex, we have this in level n, and D is given by D naught. So that means that when we have, so if say L had trivial Lie bracket, these things would all have abelian structure, these would all be abelian groups, and then there would be a chain complex we can associate to this data in a natural way. And in general, what happens is because we can slice A up into small extensions, we end up having a sort of filtration on this space, sort of filtration or fiber sequence on this space where the quotients will have that sort of abelian structure. So the things we work with aren't very far from being chain complexes, although right. So now another feature of simplicial sets. Did I start at 20 past? Yeah, okay. So I've got a minute left, so I'll just give you this one more feature of simplicial sets. So for any, we've got a functor from topological spaces, simplicial sets, called the singular functor. And what happens is, in level n, take maps from topological n simplex. Sorry, geometric n simplex. The geometric n simplex is +1, essentially. So it's exactly the shapes I've just rubbed off the board. It's things like so. And there's this functor has a left adjoint. Which is where you send denoted, so it's called geometric realization. And it's determined by, I'll just leave it at that. And so we can then use this to define homotopy groups, superficial sets. Yeah.
So maybe then.
Okay. Yeah. So I'll then just say define by naught of y. The pi naught of the geometric realization is y vertex. And this is geometric realization. And one last property I will mention is that if I say I start from a topological space, take the singular functor, and take a geometric realization, so let's set a right adjoint and then a left adjoint. So that maps down to x. This is a weak homotopy equivalence. This gives an equivalence on homotopy groups. So that tells us then that basically these two categories have the same homotopy theory. So that means so properties we have for topological spaces we can use for these. So stop there, and next time I'll be showing you what you can then do with that.